So now we're going to start to have a look at one-factor analysis of variance. So one-factor analysis of variance is where we study the effect of k levels of a single factor, where k is greater than 2. Now it's really important that we have k greater than 2, because if we don't, then we'd only have two sets of data, and we could do the paired, the two-sample normal test, or the two-sample t-test, or if it was paired data, we could do the paired t-test. So it's very important that we have k being greater than 2, so that then we have to do this test instead of any of the other ones that we've come accustomed to. So to measure the different levels of the factors effect on the measure of observation, we are using these as our hypothesis, and it's very important that we state that we're also looking at where at least two means differ, because we need at least two of the means to be different to each other for us to say that there is a difference going on. Where mu(i) is the population mean of level I, so defining what those are. Now this is an extension of the SP² formula. We're not going to look at it this way, but this is an old way of thinking about it, that we have our standard deviation pooled, and we have that within for the SW², that's within the groups. For the SB², that's between the groups, and the F statistic would be SB² divided by SW². We're going to look at it using the sum of the squares formula, which is on the next page, so don't worry too much about this. We do have assumptions which go along with one-factor analysis of variance, and these are very similar for two-factor analysis of variance and the Latin square design. So our first assumption is that the observations are obtained independently and at random of the population, that the population is approximately normally distributed, and that these normal distributions have a common variance, so that then we're telling if there is something or one of the levels that is slightly different to the others. So this is what we're going to use to end up finding our test statistic for our one-factor analysis of variance. This is what we're going to end up using to find our one-factor analysis of variance test statistic, and our test statistic is this part here, our F ratio in the end column, but we have to make this table to be able to find it out. So we're first going to have a look at how we do that using the formulas, and then we're going to have a look at how our graphical calculator can help us to do it much quicker and simpler. Now in your formula booklet you are given these formulas here, which help to remind us how we calculate it using the formulas. So we're given the SST, the sum of the squares of the totals. We're given the SSB, the sum of the squares between the groups, and the SSW, which is the sum of the squares within the groups, which is the total minus the between. So we're going to have a look at an example. So here we have different brands of light bulbs. We've got 3 different brands, and we're trying to test, we're told that they're approximately normally distributed with a common variance, so that's ticking those boxes for our assumptions. At a 1% significance level, we're seeing if there's a difference between the mean lifetime of the brands. So our H0 is going to be where mu(i) equals mu for I equals 1, 2, 3. We've got 3 brands, so our I can take on the value of 1, 2 or 3. Our H1 is where mu(i) is not equal to mu. So this here, is for all, and this is going to be just for some I equals 1, 2, 3, where at least 2 means differ. Now it's a good idea to define what your mu(i) is. It helps when you're writing your conclusion later on. So mu(i) is going to be, well, here we were looking at the lifetime in hours. So where mu(i) is the population mean, lifetime in hours, in thousands of hours, sorry, of brand I bulbs. Now, we can copy our table and then we can add on some values to it. However, just to save a bit of time, I'm just going to write the totals down here. So what we need to do is, because our brands are split into different columns, we need to have the total of column 1, so we'll call that T1. We're going to have the total of column 2, so we'll call that T2, and we're going to have the total of column 3, which we'll call T3. We also need to know the number of pieces of data of brand 1, number of pieces of data in brand 2, and number of pieces of data in brand 3. So for that, it's very simple. We've got 1, 2, 3, 4, 5 of each brand. So my N1 is 5, my N2 is 5, and my N3 is 5. For the totals of the values in the columns, we're going to have to add them up. So that's 16 plus 15 plus 13 plus 21 plus 15, which gives us 80. The totals for column 2 is 18 plus 22 plus 20 plus 16 plus 24, which gives us 100. The total for column 3, so for brand 3, is 26 plus 31 plus 24 plus 30 plus 24, which gives us 135. We also need a total and an N. So our N is how many pieces we have in total. So we've got 5 and 5 and 5, so we've got 15 pieces of data in total. And our T is all of those values added together, which we can just add the totals for together. So 80 plus 100 plus 135 gives us 315. So our total is 315. The last thing that we need before we can start using our formulas is the sum of the xi squared. So this is where we're adding together each of the values squared. So we're going to have 16 squared plus 15 squared plus 13 squared plus 21 squared plus 15 squared, so that's for the first column, plus 18 squared plus 22 squared plus 20 squared plus 16 squared plus 24 squared. That's the end of the second column. And for the third column, 26 squared plus 31 squared plus 24 squared plus 30 squared plus 24 squared. And that gives us 7,045. So we can then find our SST. So our SST is our sum of the xi squared, which is our 7045, minus t squared, so 315 squared, over 15. So our answer minus 315 squared over 15, which gives us 430. We can also find our SSB, and that's done by using the sum of these totals separately, squared, divided by the number in each one of the groups. So that would be 80 squared over 5 plus 100 squared over 5 plus 135 squared over 5 minus our t squared over n, 315 squared over 15. So putting that into our calculator, 80 squared over 5 plus 100 squared over 5 plus 135 squared over 5 minus 315 squared over 15, which gives us 310. Now we can make our table, which will help us to find our test statistic. So we're going to have between the brands, for between the columns. To put it into context, we're going to have within the brands, and we're going to have our total. And as we saw in our table before, our first column is going to be for our sum of the squares. Our second column is going to be for our degrees of freedom, which is going to help us to look up the critical value. Our third column is going to be for the mean of the sum of the squares. And our last column is going to be for our F ratio. So that's where our test statistic is going to come into it. So we need to now enter into our table what we have already found. So we have already found the sum of the squares of the totals. So that was this 430 here. So that goes into our SST. So totals, sum of the squares. We then have to fill in our SSB, which is this 310 here. And for the sum of the squares within the brands, we are going to use the fact that this is the total. And we already know this value here, so this must be the difference between them, which means that this is 120. So that's doing 430 minus 310. Next, we have to fill in our degrees of freedom. So if we have a quick look back at the table, sorry, too far back, we can see here that for between the samples, it's the number of groups that we have minus 1. So here we have 3 brands. 3 minus 1 gives us 2. For within the brands, it's n minus k. So we have 15 items in total. We have 3 brands. 15 minus 3 gives us 12, which gives us a total of 14. And if we have a quick check back, we can see that that lines up with this ending up being n minus 1. So we've done that correctly. For the means of the sums of the squares, we're going to do the sum of the square for each one divided by its degrees of freedom. So for the first one, for between the brands, we're going to have 310 divided by 2, which gives us 155. For within the brands, we're going to have 120 divided by 12, which gives us 10. And we don't have to do this for the totals. So we only have to do this for between the brands and within the brands. Now to find our F ratio, we have to do the mean of the sum of the squares between the brands divided by the mean of the sum of the squares within the brands. So that ends up giving us 15.5. So for this question, our test statistic ends up being 15.5. If we have a quick look at what we were trying to answer, it was a 1% significance level. We always treat these as being one-tailed. It's a bit like chi-squared. So in our formula booklet, we're looking at page 21, where it says F distribution P equals 0.99. And we're going to go across by the degrees of freedom between the brands and down by the degrees of freedom within the brands. And it's very important that you get this the right way around, otherwise you're going to end up with the wrong critical value. So we're going across 2 and down 12, which gives us 6.927. So as the test statistic is bigger than the critical value, that means that there is a bigger difference between the means of our groups, the means of our brands, than we would like there to be. So that means that there is something going on that's making a difference. So that means that we end up rejecting H0. So at a 1% significance level, there is sufficient evidence to suggest a difference in the mean lifetime between the 3 brands. So that's how we do it without the graphical calculator. Now luckily we do have the graphical calculator, and there's a much quicker and easier way to do this. So using our graphical calculator, if we go into Stat, this is where we're going to put our information. But first, to start off with, we're doing the same test as before. So our H0 is going to be that mu I equals mu for all I equals 1, 2 or 3, because we've got 3 brands. Our H1 is that mu I is not equal to mu for some I equals 1, 2, 3, where at least 2 means differ, where mu I is the population mean lifetime of brand I bulbs. It's a little bit shorter than before, but it's the same thing. So now, instead of finding our SST and our SSB, what we're going to do is we're going to put it into our calculator, and that is going to find that table that we had before for us. So in list 1, what we have to do is put what brand it is. So we have 5 items or 5 tests values that we have that are all brand 1. So that's 1, 1, 1, 1, 1. So we've got 5 ones. Next, we've got 5 items that are of brand 2. So that's 1, 2, 3, 4, 5 2s. And the same for brand 3. So 3, 3, 3, 3, 3, 5 3s. In list 2, we are now going to put the value of data. So I'm going to work down the columns because I've put what column it's in my list 1. So 16 is the first value in list 1. 15 is the second value in list 1. 13 is the third, 21, and then 15. And then you can see that it's gone on to saying 2. So the first value in list 2 is 18. The second is 22. Then 20, then 16, then 24. And now we've gone on to list 3, which is 26, 31, 24, 30 and 24. So I've entered all my information into my table. Then I need to go into test, and we've got this beautiful button here that says ANOVA. How many? Well, this is a one factor analysis of variance. We don't have a blocking factor, we only have our treatment factor. And we've put where it is in list 1, so what factor it is in list 1, and we've put the value for it, that dependent, into list 2. And when I click XE now, ta-da! That is my beautiful table, which has the same information in it as before. Now, to make sure we get the marks in the exam, we do have to write the table down, and it's a good idea to add in a row for the totals as well, because if you remember, we had to have our row for the totals when we did it the longhand way. So we're going to have between the brands, within the brands, and total. Now, it doesn't matter that these have flipped round, DF, SS, MSS and F ratio. And we can copy down the values. So it's 2 for between, 12 for within, 14 in total, same as before. 310 for between, 120 for within, and 430 for the total, same as before. 155 and 10 for the mean of the sum of our squares, and 15.5 is our test statistic. So that means that the TS is 15.5. Still, we go across by 2 and down by 12, so that gives us the critical value of, same as before, 6.927. And again, as the test statistic is bigger than the critical value, we would reject H0 at a 1% significance level. There is sufficient evidence to suggest a difference in the mean lifetime of the 3 brands. So you can see how much quicker and easier it was to use our graphical calculator to get our table than it was to use the long-handed way of finding out all these totals and then using the formula, and it's the exact same table that we end up with. Thank you very much.